Today we're going to use what we learned last time about taking derivatives of logarithmic functions to, to create a new technique for finding some derivatives called logarithmic differentiation. And so whenever we do logarithmic differentiation, what we're going to do is we're going to take the natural log of both sides of our equation before we try and take the derivative. And so interestingly enough, as we talked about a long time ago, we had the power rule for derivatives, right? And we said that we couldn't prove the power rule yet for all real numbers, just for natural numbers. But now, if I take the natural log of both sides of this, that would allow me to rewrite this as natural log of y is equal to n natural log of x. And now everything in here, I should be able to take a derivative of. The derivative with respect to x of natural log y is 1 over y dy dx. And the derivative of n, a constant, times natural log of x is just n over x. So we should be able to see that dy dx is just equal to n times y over x. Well, we know that y from the very beginning is equal to x to the n power. So this is just n x to the n power over x. And I'm going to note that that x in the denominator is x to the first power. And if I have x to the n over x to the first power, that could be rewritten as x to the power of n minus 1, which is exactly what our power rule said we should be able to do for any real number n. And again, in this, there was no restrictions on what the value of n could be. So we should be able to apply the power rule to any real number value of n. So if I had, for example, x to the power of the square root of 2, the derivative of this should just be the square root of 2 n times x to the square root of 2 minus 1. Even if I had a function being raised to the power of some number n, like pi, I could rewrite this as u to the pi and use the chain rule to take the derivative to get pi times u, 3 plus 5 sine x, to the pi minus 1. And then because we're doing the chain rule, we have to multiply that by the derivative of 3 plus 5 sine x. And the derivative of 3 plus 5 sine x is just 5 cosine x. So fairly straightforward here. We should now feel pretty good about using the power rule for all real numbers. But there's another good and important use for logarithmic differentiations. And that's when we're presented with a function that is written as one function being raised to the power of another function. For example, x to the power of x. And this is one function, x, being raised to the power of some other function, also x. Right? But we don't have a rule for that. Our rule for a to the x or x to the n doesn't work because both a and n represent constants. And here I have two different functions, one in the base and one in the exponent. So we're going to use a logarithm. We're going to take the natural log of both sides of this in order to allow us to pull the power out to the front so that we no longer are looking at a power being raised to another, a function being raised to the power of another function. We just have this x coming out to the front, right? So that we get natural log y equals x ln x. And we should be able to take the derivative of both sides of this with respect to x, giving us 1 over y dy dx is equal to the derivative of x times natural log of x, which is going to require us to use the product rule. So it'll be x times the derivative of natural log of x, 1 over x, plus the derivative of x times natural log of x. So we can see, hopefully, on this right-hand side that x over x is just 1. So we have 1 plus ln x. And in order to solve for dy dx, we need to multiply this by y. Well, because our original function wasn't written with any y's, and it's written all in terms of x, we need to convert back. So this is all in terms of x at the end. Luckily, we know that y is equal to x to the x. So our final answer here will be 1 plus ln x times x to the power of x. And that's how logarithmic differentiation works. Take the logarithm of both sides, the natural log of both sides, pull that function that's in the exponent out to the front, and then differentiate implicitly, remembering at the end that when you multiply by that y, you need to then convert it back to all in terms of x. So we'll do another one of these. Here we have y equals the sine of x being raised to the power of x. So it's one function being raised to the power of another function. So we'll take a natural log. The natural log of y is equal to the natural log of sine of x to the power of x, or the natural log of y is equal to x times the natural log of sine x. And again, when we take our derivative, we'll get 1 over y dy dx. And on the right-hand side, we get our first function, x, times the derivative of the natural log of sine x, which is a chain rule problem, natural log of u, so 1 over u times the derivative of u. That's the first half of our product rule for x, ln sine x. So that's x times the derivative of natural log of sine x. And then we'll add to that the derivative of x times natural log sine x. And of course, as we did last time, we'll multiply by y. I'll rewrite cosine over sine as just cotangent. So I have x cotangent x plus natural log sine x all times y. And then I'll replace that y with the original function sine x to the power of x. So we end up with sine x to the power of x times x cotangent x plus the natural log of sine of x. And that is how logarithmic differentiation works every single time, for a function being raised to the power of another function. There's one other interesting little use here for logarithmic differentiation, and that's when we are presented with something kind of messy, a bunch of terms that are all being raised to powers or being square rooted or cube rooted. That's just kind of a mess. If we had to take the derivative of this, 2x plus 1 to the 6 times the square root of 5x plus 3 over the cube root of 3x plus 1 times 4x minus 3 cubed, a big mess of a function, we'd have to do quotient rule. But while doing the quotient rule, we have to use the product rule to find the derivatives of both the numerator and the denominator. And while using that product rule to find those, we'd have to use the chain rule for both pieces of the product rule. So it'd just be a really giant mess here. So instead, what we're going to do is we're just going to take the natural log of both sides of this. So this would be like having natural log of y is equal to natural log of, well, I'm not going to rewrite it all, but all of that stuff. And the cool trick that we're going to use here now is that we know when we have something like, let's say, natural log of a times b, that's equal to natural log of a plus natural log of b. Or if I had natural log of ab over cd, which looks pretty much like what I've got here. Here's a, here's b, here's c, and here's d. I could get natural log of a plus natural log of b minus natural log of c minus natural log of d. So I'm going to be able to separate this out so there's no longer a bunch of multiplication and division going on. And in fact, as we go through that process, we'll note that, let's note that like a here is 2x plus 1 to the 6th power. So really, when we're looking at that, we're going to have natural log of 2x plus 1 to the 6th power, which we should be able to pull this exponent out into the front to make life even easier, just giving us 6 natural log of 2x plus 1. And we'll do the same with the square root right? 5x plus 3 to the 1/2 power is what that square root is, should give us 1/2 the natural log of 5x plus 3. So I'm going to open up a new page here, and we're going to see if we can just break this down all at once. So we should have a natural log of y is equal to, and our first term in the numerator was 2x plus 1 to the 6th, and we know that's going to become 6 natural log of 2x plus 1. So we're going to have 6 natural log of 2x plus 1. And we said the other one was going to become here a 1/2 natural log of 5x plus 3. So we'll have plus 1/2 natural log of 5x plus 3. And then we had a minus, and it was going to be for this one, which is going to have a power of 1/3 coming out in front. So 1/3 natural log of 3x plus 1. And then we're going to subtract the last one, which is going to be 3 natural log of 4x minus 3. And now our derivatives should be pretty easy to deal with here. On the left, we've got 1 over y dy dx. But here, 6 is just a constant now, so it's going to be 6 times the derivative of natural log of u, where u is 2x plus 1. So natural log u is 1 over u, and then you multiply by the derivative of u. So the derivative of 2x is just 2. And now we've got 1/2, and our natural log of 5x plus 3 should give us a 5 in the numerator and a 5x plus 3 in the denominator. And here we've got 1/3, and our natural log of 3x plus 1 should give us a 3x plus 1 in the denominator, and the derivative of the 3x plus 1 should give us a 3 in the numerator. And for the last piece, we've got a 3, and the natural log u should drop a 4x minus 3 to our denominator with a 4 for the derivative of 4x minus 3 up in the numerator. And all that's left is just a tiny bit of simplification and multiplying by y. And so we'll multiply all of this by that y. And so instead of writing y, I'm gonna rewrite our original function. And so our original function y was 2x plus 1 to the 6th times the square root of 5x plus 3 over the cube root of 3x plus 1 times 4x minus 3 cubed. And then we have all of the rest of this parentheses here, which is 12 over 2x plus 1. This was a plus in here. I don't have an equal sign there, but that was a plus. So plus 5 over 2 times 5x plus 3 minus, those 3's will cancel, so just minus 1 over 3x plus 1, and then minus 12 over 4x minus 3. And while it's certainly not in its most simplified form here, we have found the derivative of that original function that would have been probably a 15 to 20 minute problem of quotient and product and chain and chain and chain and chain rule over and over and over again. So that's the idea for logarithmic differentiation. It allows us to prove the power rule for all real numbers. Plus, it lets us deal with messy looking functions like this one, as well as functions where we have a function being raised to the power of another function. So that's it for this time. We've got a couple more topics left. We're going to talk about inverse trig functions next time, and then just inverse functions to finish off the unit in general. But that's it for today.